All right, hello everyone. Welcome to lecture number 15. Today's topic is choosing a database. We've been talking a lot throughout several lectures about different kinds of databases, or at least two main kinds, and about some issues and how to scale, SQL databases, and also how NoSQL databases provide more scalability. We talked last time about consistency in distributed databases, especially NoSQL databases. But today we're going to talk about some specific examples of databases that you may have heard of. And what the differences are between some of those. We're not going to cover every database because there are just dozens of them, but we're going to cover some important examples as different common choices and describe how you would process some of the reasons why you would choose one over the other. Okay. So last time we talked about the consistency in distributed database. The main key point here was after the basic lesson on NoSQL databases, how we achieve scale is by partitioning with hash-based partitioning. When we do that and we go to a large size, we start to have to replicate our data to ensure that we don't lose data, right? Because we have a lot of machines that could fail. Once we start replicating data, we have the possibility for consistency problems if the data is stored in two different places or two or more. So there's a theoretical result called the CAP theorem that says that there always is a trade-off between these three things. We can only choose two of those: consistency, availability, and partitioning. Generally, there's a trade-off between consistency and the delay of associated with accessing the database. The way that we defined a few different definitions of what consistency means. Together, they formed linearizability. And when talking about the trade-off between weighting and consistency, we found one helpful way of thinking about that's configurable in some databases is the quorum level. This determines how many reads or writes have to be acknowledged by your client before you proceed. And some databases like Cassandra let the programmer choose a quorum level for each write that or read that they do, so you can control at a very fine-grained level. Other databases are designed to use just one of these strategies. And there's a lot more to database consistency, and this is kind of an introduction to distributed systems. You can learn more about this in the distributed systems class. Okay. Now, again, we're going to talk about some real-world databases today and how to choose between them. Remember, these are the goals of a database: scalability, persistence, indexing, concurrency, the ability to do analysis, and separation of concerns. That is, having some off-the-shelf software that does a lot of stuff for you. And also integrity, deduplication, security are kind of second level concerns. We'll be talking about some of those things today as we talk about these different kinds of databases. So this table, I'm going to be showing different versions of this table throughout this lecture, where I kind of roughly classify databases into a few categories. And I give some examples of them. We're going to come back to this, like I said, many times. And each has its own use cases that I tried to summarize here at a high level. So right now, this won't make so much sense, but by the end of the lecture, this should be a good reference for you to use to remember what the difference is between these different kinds of databases I'm showing on the left. Okay. Now, there's a lot of different options. As you can see, choosing the right storage option is difficult. I mean, in general, this is data storage, not just databases, because we're also including different kinds of scalable file stores, not just databases, right? So databases are kind of like an advanced form of a file store. Okay. All right. So we're going to start off by talking about SQL relational databases yet again. Okay. And I want to emphasize this is a great starting point when you're thinking about choosing a database. A good default option is a SQL relational database. Nowadays, a lot of developers who started programming the last few years might consider Mongo as a good starting point. I think that's okay, but it's a less powerful option if you don't need that level of scale that Mongo gives you. So actually, I still think a SQL relational database is the best default choice. Anyway, as we saw here, the data is organized into tables, and you have foreign keys that create cross-references. You have this SQL language for analytics, and like, for example, select something from some tables grouped by something. So this is computing an average over a bunch of rows in a table. You could also do some filtering with these queries. It's really quite powerful. The advantage of this language is that you send this code to the database and the analysis happens inside the database very efficiently. Okay, so it allows you to run your analysis on the location where the data is stored, on the data storage nodes. Okay, and that gives you good performance as well. Another benefit here with relational databases is that we get transactions. We're going to talk a little bit more about what that means today. I think I alluded to it before. And that's a nice feature to have. Okay, it's harder to get that with NoSQL databases, with other kinds of databases. But there's a little bit of trade-off there between having that and getting scale. And this works well up to a certain size. Writes have to happen on one primary machine. Sometimes this is called a master, especially in the old terminology. And you have read replicas that give read scaling after some delay. Sharding was a way to help write scaling. And that's just a review of SQL Relational Databases. Now, like I said, it's a good default choice. Let's give an example of what a transaction is, and why this, to motivate why this is a useful feature to have. Okay, so in this case, the word transaction refers to the database actions, but the example I'm giving is actually a monetary transaction as well. And this is maybe the easiest example to think of, where you need to have multiple things happen at once. That's what a transaction is. So the example here is spending a gift card balance at a store, right? So you're like an online store or maybe an in-person store. You have several things that are happening here that as listed here. You have you're getting the gift card balance. So this is using a certain form of SQL where you can create a local variable with this @ variable name equals : equals. So we're storing in a local variable the value of the balance for a certain gift card ID. And then we're creating the order. You might have some code first that checks to see whether that balance is sufficient to handle this order that you're going to create. We create a row in the order table. After we do that, we get the order ID that we just created. For that order, we create a bunch of order details. So there are a bunch of items that are being purchased. In this case, there are 2 items. And one of them has a quantity of 3 and a price of $136. The other one has a quantity of 5 and a price of $55 per item. That together creates a cost of $683 for the purchase. So in addition, after we create this order, we want to deduct that balance from this particular user's gift card, right? So we update this gift card table that we previously read from. We do a write using this update command, where we set the balance equal to the previous card balance minus the amount that we are of this order, right? And we're doing this for this particular gift card, the same card that we read from before. At the end, we commit. So this sandwiching of these codes between a start transaction and a commit command, the semantics of that, the meaning of that is that all of these commands have to happen all at once, atomically together. That's the term we use in concurrency. You learn more about these issues, transactions, atomicity, concurrency. You learn more about that in an operating systems class, or if you just read about concurrency in general. These have to be completed all together or not at all. In other words, there should be no point in time when someone else can observe this database between steps 1 and 7. In other words, anyone who sees the database should either see it before step 1 starts or after step 7 is finished. Nothing in between. These in-between states are in the middle of a transaction, so they're inconsistent. Because there's an inconsistent state, we want it to happen all at once. But I want you to stop and think about what is it about this that's inconsistent? What problems might occur if these things were not completed atomically? If another code in the system accessed this database in the middle of this process, what could possibly go wrong in that case? What do you think? Stop and think about that. Pause and think. Well, I have actually 2 different errors that have that one's more severe than the other. So if you haven't thought about it yet, maybe see whether you can come up with 2 examples. And examples I have are, first, the card balance could be spent twice. This is the most important one. It's also maybe the hardest one to see. Because we're getting the card balance up here, and we're updating it here using the previously read card balance minus what we bought. Okay, so we took the value we read before, we create the order, and then we deduct from that. The problem is if this card balance changes between steps 2 and 6, we're in trouble. Like, this code is going to be executed by, let's say, some software that handles the checkout for the application. If you have the user checking out twice at once, and the timing is just really unlucky for us, this process could start twice in parallel. Both of the different checkouts could read the card balance. They could get the same value, like there is $1,000 on the card. And then they both create their order, and then they both deduct the cost of their order from $1,000, and they store it. But they're both doing that based on the original balance, and so one of the orders will be ignored in the balance. You see what I mean? Because the second one will overwrite the original one's balance, the balance set by the first one, not taking into account that the amount deducted from should actually be lower as a starting point. Okay, so you end up having money spent twice, giving away stuff for free, which you don't want to do if you're running a store. That's the first problem. We could also build an example where we're transferring money from one account to another, and the same kind of race condition can occur. So a race condition is another way of describing these two actions that have to, we have two actions happening in parallel, the two checkouts, and depending on the order in which they overlap or that they're executed, the output could be different. And one of those outputs is wrong by our definition of how a retail store should work, right? We're allowing an order to be created without actually deducting the balance. All right, so the second problem, a little less important, but still nevertheless worth considering, is that we have inconsistency after step 3. We've created an order. So this is an orders table. I know I went through it quickly before, but we're creating a row in the orders table that says that on this date, we have an in-process order for a certain customer. And then later on, we fill in the details of that order in a second table. So this is a many-to-one relationship between these tables. There are many order details for each order that reflect the different line items in the order. Okay. After line 5 is executed, we have a complete record of the order. But in between 3 and 4, we have an incomplete record of the order. So if another process were to check the order, they would say, yes, an order was created today, but that order is empty. Okay, so if a user happens to, with really unlucky timing, check their account status page, let's say, and see their orders, they would see there was an order placed today and it was empty. And that would confuse them, right? Because they know that they created an order with something in it, right? If the customer saw that there were no orders at that time, they would not be so bothered, because remember, the whole reason this is happening is because these two things are happening at roughly the same time, because they probably just created the order and then the split second later they checked. They would know that maybe there's some delay. That's okay. They're seeing an old version of the system. There's a little inconsistency, but they're seeing an out-of-date version of the system, but it's not really inconsistent in within its own view of the system. Okay, so this first one is a race condition. The second one is an inconsistency, and those are both problems, and they both can be solved by wrapping this up in a transaction. Okay, and the reason I'm talking about this is because this is a feature that is supported by relational databases that is generally not well supported by other kinds of databases, especially these high-scale NoSQL databases, because it's harder to implement this level of control of having multiple things happen at once when you have a lot of nodes involved where the data is split up over many machines. Okay, it's possible, of course, but it's less efficient to support this kind of feature, and therefore it's not always supported. So on a NoSQL database, transactions are less common, so I just said, because they would be slow to implement because you have machines on data split up across a lot of different machines. You need some kind of a locking to make this work. At the minimum, you need some kind of locking. So a lock is a concurrency primitive that allows you to prevent two things from happening at once if you don't want them to happen at once. In order for this to be implemented in a distributed system, you have to have a bunch of replicas that agree that there is a lock in place, and so you have to wait to acquire the lock until you get all the replicas to agree. And then your transaction runs, and then you release the lock and let someone else proceed. Okay, so I'm not going to go into a ton of detail here, but just at a high level, if we had a NoSQL database that provided an atomic conditional write operation. So this, if you have heard of test and set or compare and swap, those are CPU instructions that are provided to allow your code to implement concurrent processing without correctly, and support critical sections and like atomic operations and whatnot. Same thing is true. Because a CPU is actually something that executes a lot of things in parallel, right? You can have many cores on a CPU that are accessing the same shared memory, or even if you have just one CPU core, you could have a process that's unscheduled and another process runs. So in effect, you have a concurrency, even though you don't have parallelism. Okay, maybe that's too much talk about operating system stuff. But anyway, in a distributed database, you need to have an operation like this. So I have the pseudocode for it here, where we have two operations that are kind of bundled together. We're considering our NoSQL database to just be a key value store where we have a put and a get operation. But we have the special combined put and get, where it will put a new value under a key if and only if, when we get the value of the key, it has a certain old value that we expect, okay? And we call this a conditional write operation. Okay, so the benefit of this is that we're doing both a read and a write at the same time. If you can implement that in the database correctly, this allows you to implement a lock, which lets you implement a transaction. Okay, like I said, a lot of NoSQL databases support this, like Cassandra and Mongo are examples that do. So using this primitive, here's some pseudocode on the right-hand side that implements a transaction on one of these NoSQL databases. We have a bunch of clients that have their own unique IDs. They're all just hard-coded. I'm just giving the simplest possible example, basically. The code, what this code is implementing is the deduction of $1 from an account. So there's a key and a value that corresponds to the balance of an account. The key is called balance, and the value is the dollar amount. And we want to make sure that even though a lot of different actors in parallel are deducting from this account, and they have to do two things to do that. They have to read, and then they have to deduct. They have to do a subtraction internally, and then they have to write back the smaller value. And if there's, if these are happening in parallel, then the reads, the timing of the reads and writes could be such that it causes this like overwriting of deductions, like we just saw before. So we need a transaction, we need the read and write to be between a transaction. This code down here is the transaction where we're getting the value of the balance, we're storing it in a variable x, and then we're storing x minus 1. So we're doing some operation to it, modification of just a minus 1, and storing it back. These two things cannot be interrupted. We don't want anyone else to come in and read the balance before we get a chance to update it, and then that person in turn to update it with their own value. That would be wrong, right? So in order to implement this, we have a lockup. We have a lock implemented here in this loop, and then we release the lock. What the locked code does is it checks it reads from the database to check the value of the lock, and so we have a special key that's dedicated to basically assigning which of the clients at this time has exclusive access to run the transaction. In other words, they have acquired the lock. So the value should be, if the value is equal to 0, then no one has the lock. If the value is equal to your own ID, then no one else should be able to access the lock. So the way this works is you have a loop that reads the value of the ID, and when it's not equal to your own, in other words, you're not holding the lock, then you try to acquire the lock. You do this with this special atomic conditional write operation that I introduced before, where what you want to do is put your own ID, which is 37, into this key, under this key, but you only do that if the current value is 0. So it's if get lock equals 0, you put lock ID 1. I guess actually this would be a lot easier to read if it were reversed. Or I guess this is like sort of like the Python syntax that some of you might be familiar with. But anyway, these two things go together. Okay. So the reason why this is in a while loop is because we don't know whether this proceeded. This could either succeed or fail. We might either store our ID there or not, depending on the what we read, and then we repeat the loop if we failed, which is to say we did not store our ID there. Okay, that's why this loop is here with this conditional. We might have to keep trying if we have others who are if you either have someone else who's holding the lock permanently or for a while, or you have others who are have recently acquired the lock. Either way, you'll just keep waiting until eventually someone releases the lock. The way to release the lock is to just store the value 0 under that key. Okay, so you acquire it, you'll end up looping until you can acquire it and store your own ID under this key, and then you do your transaction, which is to these two things to have to happen atomically, and then you release the lock. And you also would need to protect any reads to this data if you want this. If you don't want people to see this state inconsistently, this kind of locking, lock acquisition and release, this transaction has to also surround the reads as well as the writes. Okay, but I don't want to I can't get too much into that because it's a complex topic. Like I said, it's covered in OS class. But I hope that gives you an idea of what transactions are, a little bit about concurrency in distributed systems, what locks are, and also how these are supported in some NoSQL databases. Okay, but keep in mind, though, that this operation that I have in purple, yes, it's supported by Cassandra and Mongo, but it's much less efficient than a regular get or put, because the read it's doing has to be done on all the nodes in a consistent way. Okay, so there's a little bit more network communication that happens there. Okay, coming back to our list of databases, the first one we just talked about were the SQL Relational Databases. These have some throughput, some scaling limitations in the sense that you're only writing to one primary node, or you're sharding, which sometimes is not really possible. Or if you do, or if your sharding doesn't work well, then you have to read from all the nodes at once. So like for many reasons, scaling of relational databases is not perfect. Is not doesn't really solve all our problems. Okay, so we have all these other kinds of databases that are much more scalable. Finally, at the end, we have some networked file systems also have the same centralization as a relational database, and therefore they're not super scalable either. We'll come back to those later, though. Okay, so for the rest of the lecture, we're going to talk a lot about these different kinds of scalable stores that use usually some kind of hash-based partitioning of the data. Okay. Now, one of the key things in this topic of choosing a database is understanding that different databases are designed with different data abstractions or different data models in mind. And very often that's what drives your choice of the database. And also it drives what the choices that the database makes internally, in how it stores things, how it accesses things, what's fast, what's slow. A lot of that comes down to differences in data abstractions. Okay, so we've already seen tables, rows, and columns that are used in relational databases. I actually am listing two different kinds of relational databases. These are highly structured data models. You have to define ahead of time what the tables, rows, and columns are. The second type, column-oriented databases, I'm going to talk about briefly now, and then I'm going to spend more time talking about the more varied different data abstractions supported by the NoSQL databases down here. Okay, and you'll notice that's I think that one of the key differences between the different NoSQL databases is the type of data abstraction they provide. Very often, so these are semi-structured data values in the sense that you don't have to define ahead of time what structure they take. Nevertheless, there's certain patterns they have to fit into and certain styles of defining the data, which is different depending on what database you're using. Okay, and it's also true of file systems are another kind of data abstraction. With a file system, you have the key is kind of the file name, and the file contents are a big blob of data. Okay, so this is kind of a very simple key value abstraction in a distributed file system. But with the NoSQL databases, we get more than a simple key value, as we'll see. We'll be able to store under the value a lot of some semi-structured data. Okay. But first, a quick overview of column-oriented relational databases. Again, these use tables like the traditional relational databases we've seen. And they use the same SQL language for querying. The only difference, though, is in the way they're implemented. And they're optimized because they're optimized for different kinds of workloads. So what we've seen previously are actually databases that are optimized for online transaction processing applications, OLTP. For example, like most applications involve a lot of users accessing it at once. We have a lot of parallel reads and writes. Each one of those reads and writes is pretty small because it involves an individual user action, a transaction of some kind. This is transaction in a different sense than, sorry, this is a little confusing because I'm not talking about atomic transactions here, but just like reads and writes. And for that kind of workload, we have relational databases for modeling the data, and read replication and sharding allow you to scale out the reads and writes. Okay. Now, that doesn't quite work for this other kind of workload, which is called OLAP, which is online analytics processing. So analytics and transactions are different in the sense that with analytics, what we're doing is just a few huge queries that kind of work over the full data set, rather than doing a bunch of little reads and writes that add to and access little pieces of the data set. Okay. So an example of this might be if you're a retail store, like let's say Target, you want to know over the past 3 years which store locations have customers been the most responsive to our mailed to home coupons. So this would involve a query that goes through all the purchases over 3 years for this national chain, and all the mailings of the coupon mailings, and does like a correlation between the two to figure out in what location, and also like a sorting by location to figure out where the correlation is best when grouping by location. Okay, so it's a pretty complicated thing. It has to go through all of the purchases and lots of other data in the whole data set. Okay, because you're doing in these analytics queries, you typically have to scan through the whole table, not just use an index to find a particular like one piece of data using an ID. Like very often with transaction processing applications, like let's say social media application, you want to find all the information associated with a user or with a post or something. So you have some kind of ID that you can use with an index to just zoom in, to skip to quickly the data you need. That's not so with these big analytics queries. You need to scan everything. And so you'll need to parallelize your query over many nodes to make it efficient. You can't fit all the data and you can't run the computation efficiently on one node. So you do need to do some kind of scaling. But it's a different kind of scaling, and it's a different architecture with different optimizations, because your workload is mostly reads, not writes. So you can do things like replicate data without worrying about consistency, and you have to, And also you can store the data differently. So column oriented, it refers to the way the data is organized, which is a complicated topic. There's a good article by I think Madden and Stonebreaker and it's some Bazi or something. Anyway, so column-oriented databases really have different internals for storing the data. You don't, rather than storing data like one row by row, like you store it like all the data for one column together, and then all the data for the next column, which is kind of weird, but it's efficient if you're scanning through just a few columns of data and all the rows for that column. It's best to put all that row column data together. But again, we can't go into details of that. We don't need to go into details of that. Just know that it's another kind of relational database that handles the same kind of queries. Very often you'll have two different databases for your relational data. One is your live database that is an for your OLTP applications that's actually handling creating new data and is backing your applications. And then you have a lagging read replica, which is the OLAP database, or it's also called a data warehouse very often. So you might have the data from yesterday and earlier in this other database. It doesn't have to be totally up to date. It can lag behind. And you're mostly doing reads on that's scanning through all the data, and the database is organized in a different way to make the scans efficient. Okay. That's a column-oriented database for OLAP applications. Okay. So finally, we get to what I think is the core topic of this lecture, is choosing between the different NoSQL databases that all have different kinds of semi-structured data values, and they're all highly scalable with hash-based partitioning. Okay. And again, the best choice here depends on the type of data that you're storing. Okay, so we're going to show I split these up into 4 big categories. I mean, this is kind of an arbitrary grouping, but it's the best I could do to come up with like 4 easy to understand flavors of NoSQL databases that will give you a good idea of what's out there. Okay, and this comparison is based on an article here that you can read more, but I'm hoping to summarize the most important parts here. I'm going to start off with Mongo, which is very popular, especially for applications that are using JavaScript in the front end and the back end, because what Mongo stores is JSON objects, which are JavaScript object notation objects. So the data if what you're storing is a JSON object, or what the data you're storing can be represented as a JSON object easily, then MongoDB is a good choice. The sharding key, which is a special key called _ID, which determines which node it goes to. That's like the hash partitioning key. And then you can have whatever else you want in the object that stores the data. Okay. And the key things about this is that, yes, it stores JSON. I mean, any key value store can store strings, and any string can store JSON. But the cool thing about Mongo is that it's really designed to understand JSON, and so that if you modify a little piece of the JSON, you can send that update. You can send just a small update, and the update doesn't have to modify the whole JSON object, but it's just a little piece that changed. And it also keeps a history of changes, can keep a history of changes for that document. So we call it a document store in the sense of like JSON documents, and it works well for even pretty big JSON documents where you're updating little pieces, and those are all stored under one key. Okay. A lot of developers have made this work for a wide variety of applications, but yeah, it's a pretty basic model, and I think its upside maybe is the simplicity. Key value store, values JSON. You can modify pieces of JSON efficiently, and access pieces of the JSON efficiently without, like, for example, if you have a huge JSON document, and you can do a get without fetching the whole JSON object, but just a piece of it that's stored under a subkey, of that JSON object, if that's what you want. Okay. More details here. Actually, this is actually kind of copied from that blog post, so I'm not going to go into that. The second kind of database I want to talk about is ElasticSearch's example of a search engine. It's actually pretty similar to Mongo in the sense that it also stores JSON documents. But the difference is in the way it indexes. So instead of just having one primary key to index, it's designed to index every word in the document and to handle advanced queries on those words. Now, of course, if you're enrolled in this class and you've done the project, you know that this can be used to build a search engine, like we used it to build a news article search engine. So any one of these words, so for example, this is a news article that I found in a previous semester teaching this class, where the word Tarsia, my last name, appears. Some person I don't know, somewhere in New York, was quoted in a news article. Okay, so there's no key for Tarsia, but I can still find this entry quickly because when you insert this data, what Elasticsearch does is breaks it up into words and indexes this document underneath each one of them. So actually, it does use hash-based partitioning on the, but it does it on the individual words in the document. Now, actually, you could stop and think about how to implement Elasticsearch using a simple distributed hash table. We'll see that like Redis and Cassandra are examples of those, which we'll talk about later, or even Mongo. How would you implement this using a distributed hash table? For example, if you wanted to be able to search for the documents that matched the words Watertown and the word gift. Well, the basic solution is called an inverted index. For every one of these, and I kind of just described it, you break up the article into words, and each one of those words is a key under which you should store a reference to this article. Now, of course, each one of these words, like donations, is a word that appears in not just this article, but lots of other articles. So the key donations will not just point to this article, but will point to a list of articles, including this one. So when you add this article, you have to add this article ID, whatever key you have for this article, like let's say the URL, that URL would be listed underneath that list of documents that have the word donations, and same thing for buy and lunch and so on. Okay, so this actually involves a lot more indexing than Mongo does. So you would choose to use this instead of Mongo if you need that level of more advanced indexing. You don't care about the inefficiency compared to just indexing on a single key. Now, this gives you more features than Mongo in terms of searching, but you pay a cost for that, right? There's a lot more indexing. When you write a document, there's a lot of places where you have to create references to this document based on the number of different unique words there are in this article. That's the only way to efficiently search through a huge list of articles, right? You have to have a lot of indexes. Okay. So the main point of this is for advanced search. You can define flexible fields, and actually you can do queries that match not just words, but like words in particular fields and whatnot. So actually, using a Lucene query syntax, it's pretty complex, and the implementation is a lot more complicated than just having a simple inverted index that I talked about, in order to support the different kinds of queries like ands and ors and nots, and searching under different fields, not just across the whole document. Okay, so you'd use this when you need to do full document search, and you can make other applications fit this. In cases where you need to search on a lot of different variables or terms, you can make this work. Okay. Cassandra is another NoSQL database. So third category, what I would call this a 2D key value store. We'll see that DynamoDB is another example in the same class. It's worth pausing on this because this doesn't just store JSON underneath. It has a very particular way of storing data underneath the keys, which is essentially another key value store. So underneath, for each row key points to a value, but that value is a dictionary, essentially. And the keys in that dictionary are called columns, column keys or column names, and they have values. Okay. So the point of this is to model something like a relational database table, except the particular columns assigned to each row are not predefined. They can be different for each row, because each row points to its own, essentially, hash table or dictionary. Okay. These column names are indexed, so you can efficiently get, this could be very long with thousands and thousands or even millions, I think, of column keys. And you could efficiently just get one value underneath because, it's a dictionary you can implement with a hash table or a tree-based index. Or, Cassandra can implement it that way. You as a programmer using this don't have to worry about that. You just have to know what structure is and how to use it. Okay, there's an article here from eBay about how they model their data on Cassandra to give some best practices. That's a good reference here. Another example here for Cassandra, this is showing information about bridges, like physical bridges for roads in the world. And again, notice we have rows. This is showing different examples of rows. There's a key for each row, and then there's some columns. So, and you can think of this peach area here as another dictionary underneath the big dictionary. Okay, this is the second dimension of dictionary. It's a 2D dictionary or 2D key value store. Different rows can have different columns. Notice that, and we have two different classes of objects. So this first one is I don't know what this is actually, but it has a different set of columns versus this other one. But it's all within one big table. So it's kind of like having two different tables with different schemas, but it's all within the same storage system. Okay, the same Cassandra database. And you can define these on the fly without having to predefine them. Okay. So I would describe Cassandra as a NoSQL database, but also a 2D key value store. Maybe would be a better way to describe it. Sorry. This is a very scalable design, more so than let's say Elasticsearch, because there's a minimal amount of indexing. And this is a good choice when you can make that minimal schema, the minimal data format work for you. You don't necessarily need huge JSON objects like Mongo gives you, but you're okay working with 2D dictionaries inside dictionaries. DynamoDB is another example of a 2D key value store, very much like Cassandra. There's just a little bit of a different set of terminology and some slight differences in the implementation, of course. But mainly, I want to focus on the terminology so that if you run into this, DynamoDB is Amazon's distributed NoSQL database that they actually wrote a very influential research paper on this about 15, 20 years ago, something like that. 15 years ago, I think. On DynamoDB, yeah. And that kind of, in some sense, was one of the two papers, in addition to the Google's Big Table, that spurred the NoSQL revolution. But Dynamo more than the others, actually. Anyway, so with Dynamo, we also have these rows that can have different types of data stored underneath them, just like with Cassandra. So on the right hand side, I have Cassandra repeated for comparison. But instead of column names, they use attributes as the terminology for those different things stored underneath the key. And also, they introduced this new concept of a sort key, which is kind of combined with the partition key to create the primary key. So the partition key is what is hashed to determine which node the data is stored on. So this is how the hash-based partitioning operates on the partition key. But for a single value of the partition key, you can have multiple sort keys, and those are sorted when they're stored. You can efficiently do range queries on those as well. So you can have so it gives you a little bit more. You don't have to have a sort key, so you could actually eliminate this, and that would leave you with something that's very similar to Cassandra in the model. But there's this additional option for the sort key. And that's especially good. And you don't necessarily even need attributes. For example, if all you want to store is a sort key, but that would be a very minimal kind of data that would work for that. Okay, there's a blog post here that describes the partition key and sort key, how that works in Amazon, which is worth reading if you want to learn more about that. Right. Okay, so now the fourth kind of NoSQL database, I think this is the last big category I want to talk about, is the cache. And in particular, I'm using Redis as the example. So you can call Redis a database or you can call it a cache. And we'll see that there's these big distributed caches that are kind of this special types of databases in a way. Okay, so it's still a big key value store that uses hash-based partitioning, lots of nodes to store data. The value actually in this case can be one of many different types. So you can use, for example, actually I don't know if you can use JSON, but this list doesn't show it. But like different. You can use a dictionary as the value, so that would be something similar to Cassandra, or a list, or set, or just a plain string, or bitmap, whatever. And there are specific operations that are custom to each one of these things. Of course, you could represent any one of these as a string, but the reason why they provide different specialized ways of storing these is because they're efficient custom operations that are tailored to these that let you, for example, add to a set. You can do that without having to read the whole set in and then make a modified listing of it and store it back. That's what you'd have to do to represent a set as a string. Okay. But the big difference between Redis and the other NoSQL databases is that it's really optimized for storing data in memory, in RAM, not just on disk. And it's optimized for high performance rather than for persistence primarily. Okay. All right. So we call these distributed caches. These include Redis, Memcached, Memcached, ElasticSearch, and Riak, or Riak. I'm not sure how that's pronounced. They're called caches because they originally developed to store data temporarily, and particularly to reduce load on relational databases. So they're kind of not transparent caches, but managed caches. Because it's a distributed cache. So one node can access something from a relational database and store it in the distributed cache so that others can access it. Okay, and because it's stored in memory, it's fast to access. These data elements always support some kind of expiration, so that's another feature that's different compared to traditional other kinds of databases. Expiration is definitely something you need in a cache. They're distributed across many nodes. You still have the same data consistency issues that occur in other NoSQL databases where there's distribution. Well, these are optimized to do things in memory. Okay. The interesting thing, though, is that they're not... Originally, I think they were designed to only work in memory, but over time, they've evolved to also support storing data persistently to disk. So that once they started doing that, then they kind of became databases. But originally, their main use case is not for persisting data permanently, but for storing temporary data, for caching data that's going to expire, and that should be quickly accessible from memory. So these are similar. These distributed caches are similar to NoSQL databases, not totally the same. So if we want to just do a high-level comparison with a NoSQL database, the items are always permanent and persistent. They can be cached in memory for high performance, but they're always stored on disk for that persistence. And the main goal is scale. Whereas with a distributed cache, items can expire, so they're not necessarily permanent. They are stored in RAM for sure, but sometimes they're persisted to disk. So it's like more like both of these use disk and RAM, but they have different priorities on whether they're first. So databases are kind of disk first, and caches are RAM first. Speed's the primary goal of a distributed cache, and once your RAM capacity is reached, you can start expiring the least used items or the oldest items. That's the kind of cache behavior. That's what makes it different than a database, I guess. But in many ways, it's the same idea. You still use hash-based partitioning. You still have consistency issues. And again, you can also persist the data if you want. You don't need to have it expire, depending on how you configure the distributed cache and depending on which distributed cache you're using. Okay. We also, this term cache is one that we've used before. So I want to do another comparison between a reverse proxy cache, which is to say, for example, a CDN, and these distributed cache database things that we're talking about. So what we're talking about now is like I said, more like a database, whereas CDNs and reverse proxies, these caches are often transparent to the application. They most commonly operate at the HTTP layer transparently, so you just kind of insert them in the middle of an HTTP interaction between client and server, and they cache those responses. All you have to do is configure the cache's origin, and they work there. So they're transparent caches, and they're specifically oriented toward HTTP, whereas these distributed caches are managed at the application level. They can store like user-specific information that might be reused. Like if a user logs into a system, their username and password and session key might be stored in a relational database. The cookie that is used to authenticate each request, traditionally you might have to check the relational database each time a request comes in to see whether that cookie is valid, but that's slow, right? You don't want to put that load on the database. So one thing you could do is have a distributed cache that stores all the recently used users' cookie IDs, have the cookie as the key, and therefore you can map to the user information there instead of checking the relational database to check cookies. Okay, that's a very good example. Another example might be another caching thing might be a leaderboard that's in a header of every HTML page. If you're running a game website, and at the top you always show like the same thing for every, there's something that's updated but it's shown on every page. You could cache that in a distributed cache and it'd be available to all the different clones of the application server that was running. Okay. So Redis is an example of distributed cache. It's really optimized for speed and less so for persistence. If things fit in memory, then a cache is a good choice. And it's also a good choice when you're caching data that can be rebuilt from another data store. So often this is like a redundant type of storage that's added really just for performance reasons rather than being the main data store. Okay, and there's some more details here. Okay, so we covered all these ones that are grayed out on the top. What's left to talk about now are the file systems. Okay, several different kinds of file systems. I've grouped them into cloud object stores, clustered file systems, and network file systems. All of these, of course, have file names and file contents as the data abstraction. The way file names are used is a little bit different for networked file systems, so it's basically the same thing. So the main difference then is in the way that these are used rather than the data abstraction. I'm going to start with networked file systems because this is maybe the most unusual one, maybe and the most difficult to understand. What these are file systems that are available to an operating system but are not on the machine, but refer to data that's on a different machine. So you may see this if you're using a university campus computer and you log in and you see like your home directory that has your data. That might be data that's shared regardless of which computer you're using. That data is stored in a central file server, an NSF server perhaps, or SMB. So the NSF is the network file system for Unix. SMB is the same thing for Windows, different protocols. I forget what SMB stands for. And so you have a file server that has maybe a RAID configuration with lots of disks that stores a bunch of data, and it runs a service which exposes a network interface for other machines to access those files. Okay, so this uses a specific protocol, whether NFS or SMB, and you have to have permissions to access it. And you have a bunch other machines can configure themselves so that certain folders on the machine actually refer to data that's on that remote server, right? So in this case, I have some files, most of the files on the system, let's say in my home directory, those might refer to data that's on my disk physically in the same machine, whereas there could be another folder that is linked by the operating system through a network file system module. Whenever I access those files in the folder, a request is made over the network to access the file on the other machine. Okay. Yeah, so this allows an application. Notice that this application that I run here, this green application, it can just access the files using local file names. It doesn't really know that some of these paths, some of these folders are translated by the operating system into requests to a remote machine. That's the cool thing about this, right? So we can write an application, a very simple application, the kind that you would write in an intro to programming class that accesses some files on your machine. Yet, if the operating system is configured correctly, those operations can actually involve a distributed system where the files are being stored on a different machine. Okay. Now, this is not too common with modern cloud-based applications because we usually don't have our applications interact with the local file system. Instead, we have them interact directly with some kind of networked system. Okay, so I'm showing this as an example of something you might see in an old style application where you have an old application that was designed to write to local files, but then you want to migrate it maybe to the cloud or scale it up to have larger storage. You can make that storage available on a different machine or in the cloud or something and connect it through one of these networked file systems. Now, the sort of cloud-native way of having distributed file systems is with a cloud object store. An example of this on Amazon is S3, okay, which I'm sure you've seen and heard of. We've used in this class for the projects. So this is a general-purpose file store for cloud applications. The cool thing about this is that the capacity is basically unlimited. I mean, of course, Amazon, like on their side, they have to worry about having enough disks to meet the capacity, but you're sharing that capacity with thousands of other companies, so you're not really going to run out of capacity in practice. And there's a network API for accessing files, and you write your applications to use that API. Okay. One of the other cool things about this particular cloud object store and the other ones like it are that it has a built-in web server that allows you to configure your files to be public if you want them to be, and then you can anyone around the world can make a GET request to a particular URL to access your files in this S3. They call it a bucket, which is like a folder kind of. Okay, so for example, on my homepage, I have a folder here or a page localization that has some like data and results from my PhD thesis. So, this is data that I generated like 10 years ago, and it's pretty big. So these files are like in total about 10 gigabytes, which certainly 10 years ago was a lot of data, but even today it's a lot to store on a web server. So instead of storing them directly on this web server, so the smaller files are hosted from the same web server. You can see that the link refers to a file name that is relative, so it'll be the same path. So it'll be like stevetarsia.com/mobisus11batphone, whatever. But these other files down here, the really big ones, they have absolute URLs that refer to S3 on Amazon, the Starsia bucket, and then a folder that stores this big file. So these many gigabyte files are accessible through Amazon S3. I don't have to store them on this web server. This web server can be small. and the files are stored externally. And this is often done for like images and other big resources, videos that websites host. Very often they are on an S3 bucket. And if you look through the source code of pages, you'll see a lot of references to like S3, for example, for images and whatnot, other kinds of media. The last example of a file system, a distributed file system I want to talk about very briefly, is the Hadoop file system, HDFS. Now, later on in the class, if I have time, we're going to talk about Hadoop and Spark, which are distributed processing and analysis tools for running code in parallel. Now, in order to have code that runs in parallel on a lot of machines work efficiently, the purpose of that code is to do a lot of analysis, to read through a lot of data. For that to work efficiently, the data needs to be distributed on a lot of machines so that it can be read in parallel, and the code that's doing the analysis has to be running on in the same location as where the data is stored, because you want to minimize transfers, external transfers. If you just want to transfer internally from the solid state drive, let's say, to the CPU directly, rather than transferring it over the network to some other machine. Okay, so HDFS is a file system that's designed to work with Hadoop for doing these parallel processing. So with a Hadoop distributed file system, it's designed to work with the distributed processing tool to run parallel analysis. So if you have files that are going to be analyzed offline in huge parallel processing jobs, you might want to create an HDFS cluster for those files and store them there. But the data abstraction is files. It's not like a relational database or a NoSQL database. Okay. All right, so these were several different kinds of data stores. I think the main way that you're going to choose between them is by thinking about what the structure is of the data you have and what pattern of access you have. Okay, for highly structured data, we have relational databases, and these are especially the traditional row-oriented databases like MySQL. These are less scalable than other designs, but they're good default choices if you don't necessarily need huge scale. Even though they provide a highly structured data abstraction, you also could store key value data in here if you really want to. If you want to design from the beginning with scale in mind, you can use one of these NoSQL databases that stores semi-structured data. Mongo is very popular. It stores JSON. ElasticSearch also stores JSON, but it has more indexing, so it's less efficient for the same amount of data, but it's easier to find data. Redis is a key value store where the values can be different types. It's optimized for caching and stores data in memory primarily. And then the Cassandra and DynamoDB are 2D key value stores, which I think are the most scalable of all these designs, actually. I don't know if I mentioned that explicitly, but they are, because they have the simplest structure. You have dictionaries stored underneath this big global distributed dictionary. Finally, we talked about different kinds of key value stores. Especially these cloud object stores like S3 and Azure Blobs, these are basically like variations of distributed databases that don't have any internal structure apart from just big data blobs being the values. Okay. All right, I hope that was useful. It's a very complex topic, and this is just meant to be an introduction. And so, try to keep up to date as new ones come out, but you're never going to know the details of every database out there, especially these days when there's so much innovation happening in databases. But it's good to know at least these ones as good examples of what's out there and what's kind of popular. All right, see you later. Thanks for joining.